Gehly's coming up right now. He has done his PhD in Colorado and is now postdoc at University of New South Wales in Canberra here, and is going to follow on with the theme, which is the separation of the M2 and doing some analysis on the results from how that stabilization worked. Over to you.
Great, thank you. Good morning, everyone. So as mentioned, I'm going to be kind of following on from the previous talk and specifically looking at some analysis of that separation maneuver and trying to estimate the change in velocity that we achieved. So a brief overview of the mission again. So the M2 satellite launched as two 6U satellites that were joined together as a 12U. We launched 1 year ago, and so we've been on orbit for that year. We did an on-orbit separation maneuver in September, so about 6 months in. And as you can see, we've got a picture on the bottom left of the satellites as they're being put together by our flight team, and then a picture from on orbit as they were doing that separation maneuver. Ever since then, we've been operating this drag-controlled lead-follow formation, as Brenton mentioned. We're also part of what's called the Falcon telescope network. So we have some telescopes here on the ground. We operate one of these nodes at UNSW Canberra, but there's also a global network of telescopes that's managed by the U.S. Air Force Academy. So the good part of being in this network is that we're able to access any of these other sensors. So anytime that one of them is available, has good visibility conditions, good weather conditions, we can use that to track our satellites and do some analysis. So the main telescope that we actually use for this is located at Colorado Mesa University in Grand Junction, Colorado, and that just happened to have the best observability conditions for this particular project. So we've got a number of different research objectives that we're trying to accomplish with this mission. The main one that I'm going to focus on today is about being able to detect and characterize changes in spacecraft behavior while they're on orbit. So that's a really broad area of research that could encompass stuff like changes in attitude, if a satellite's being actively controlled, and then the next time you observe it, it looks like it's tumbling or spinning. That could indicate some kind of malfunction. It could include deployments of solar panels that would make the object bigger and brighter, stuff like that. But in particular today, I'm going to focus on detecting this maneuver where we split into two objects and being able to characterize that change in velocity or delta V that we had when we did it. So in the first instance, we were able to get some pictures from this telescope. So this one's taken about 5.5 hours after our separation maneuver. At this time, we were tracking in sort of a satellite tracking mode, so the stars show up as streaks in the background, and the satellites show up as dots. So the orbital motion in this case is kind of diagonal towards the bottom right, and at the time that we took this picture, M2B was actually in the lead, and M2A was about 1,000 meters behind. And so we're able to nicely detect that we've got this change. We've now got two objects where there was one. And by collecting several of these images over time, we're able to actually compute that delta V change in the orbit. So what are the challenges in doing maneuver detection? So broadly speaking, with estimation problems, our first challenge is that we're not directly observing the states. If we want to know what the position and velocity of the object is, we're not in general directly observing those XYZ positions. So in the case of optical data, what we're getting is angular measurements. We know where the telescope is pointing when it's taking this image. We can use like an azimuth and elevation angle, or equivalently a right ascension declination for inertial coordinates. We know where the center of the image is. We can count pixels to see where the objects show up in the image. And so we can get an angle pair for each object that's present. Those measurements are not going to be perfect. We've got some noise and bias that are contributing to errors. We've got nonlinear dynamics to predict the motion in time. We've got nonlinear measurement equations. Some specific challenges for LEO optical space situational awareness. We've got sparse data. So I've actually plotted the measurements that we collected over time here. And what you can see is for most of the time, we're not getting any data. So the satellites are passing overhead very quickly. In this case, we were able to get one pass about 5.5 hours after the separation. We got 18 observations during that pass over about 1.5 minutes. Then we had about a 24-hour gap before we were able to observe again. We got 6 observations during that over a period of about 40 seconds. So that's sort of what we're looking at here. We're also getting angles-only measurements. We're not getting any range data, so that's not helping us. We've got some dynamic model errors. Being able to characterize the satellite drag that we're experiencing is a really difficult thing, and we know that we're going to have some errors to go along with that. And then specifically for this, the big change that the big challenge that we're facing is just that we're trying to detect a very small change. So we're looking at a delta V that's on the order of 10 millimeters per second, and trying to observe that and characterize that's going to be a challenge for us with this sparse data situation. So we looked at this in a few different ways, and sort of the first thing I did was take a direct approach. So we've got these angle pairs for each object individually. We can use that to estimate the full 6-dimensional position and velocity for each object. If we look at the difference in velocity, just subtract them at that time of separation, that's going to tell us what our delta V is. So to kind of test this and see how feasible it is, I set up a simulation. And so I wanted to see, in a controlled environment, when we know everything, we have the truth data, how well can we do with this? So looking at a sparse data situation where I'm actually giving myself a little bit more data, so I'm giving a 12-hour gap, another arc with some data, a 12-hour gap, and another arc with some data. I was able to compute this orbit solution, and we're looking at errors of about hundreds of meters in position and hundreds of millimeters per second in velocity. So because the change that we're trying to detect is actually smaller than this isn't going to be a viable approach for us. We just don't have enough data in this situation to be able to compute the change that we're looking for. So this direct approach isn't going to be feasible for us. But we don't actually need the full inertial position and velocity in order to solve this. What we're really interested in is the relative motion. So we could reset this problem and reformulate it using some relative positions and relative velocities between the objects. And the first thing that we need to do is define a coordinate system that's going to work with this. So we can define this relative coordinate system called RIC for radial, in-track, and cross-track. The radial direction is going to be our x direction. That's just pointing from the center of the Earth straight through the object. Y direction is in-track. So that's pointing along the orbit in the direction of our velocity. And then the z direction is cross-track. So in this picture, that would be out of the page. And we've got these equations called the Clohessy-Wilshire equations that give us our relative positions, and we can also get some relative velocity equations from this as well. The one thing that I want to point out here is we've got some periodic terms. So we've got sine and cosine functions, and what we can see from that is if we've got separation in just x or just z, it's going to grow over time, and then it's going to come back to 0. So that's not going to give us separation in the long term. The only thing that's going to give us separation in the long term is changes in the y direction. So if we've got some velocity imparted in that in-track direction, in our velocity direction, that's what's going to give us the growing change over time, like Brenton was mentioning. In total here, we've got 6 parameters that we're trying to estimate. These fill in these integration constants in here. I put an asterisk because we're actually going to reduce that a little bit further again. So we've gone from trying to get 12 pieces of information down to 6. So the other thing that we're going to do to help us reformulate the problem is use a relative angular diff between the two objects. So I'm going to define this new angle delta. That's just the angular separation between the two objects. So rather than using angle pairs off of each measurement, we're just going to use this one delta measurement to try and estimate our velocity. We're also further going to constrain the problem a little bit. So we know at the separation time the two objects were joined together. So those separation positions were all equal to 0. So we can immediately eliminate 3 of those parameters that we're trying to get. And now we're down to just trying to estimate our 3 initial velocity components. And apologies, the equations got a little bit messed up there. But all we're trying to get is our initial velocity in x, y, and z at the time of this separation. So we've reduced our problem. We were initially trying to get 12 states. Now we just need to estimate 3 states. So this one also didn't work. I set up a feasibility study again, just doing a simulated maneuver, using that delta angle for separation. And very similar to before, we're getting position errors on the order of hundreds of meters, velocity errors on the order of hundreds of millimeters per second. So once again, there's just not enough data here, and it's not sensitive enough to be able to detect the very small changes that we're trying to do. So this one's also not going to be feasible for our real data scenario. So what I did, just to constrain it a little bit further, we know, as I mentioned, that the main thing that's going to drive our separation is that change just in the y direction. The changes in x and z are going to be periodic. They're going to go back to 0 over time. And so I said, let's set those equal to 0 as well. And now we're just going to estimate that change in the y direction. And so with the problem fully constrained like this, it's relatively easy to get a solution. For each of the 24 observations that we had, we're able to directly compute an equivalent change in velocity in that y direction at the separation time. And we've got a pretty nice plot. So this is just looking at the individual data points. The mean for this came out at 19.7 millimeters per second, standard deviation of 0.2 millimeters per second. So pretty good sort of spread on that. And we were able to compare the solution against our GPS data and get a more precise answer from the GPS. And the GPS was 19.92 millimeters per second with a standard deviation of 0.02. So these two solutions are within one standard deviation of each other, which is a pretty good match and good agreement for us. So just some closing remarks on this. So using this relative state formation and looking at the Clohessy-Wiltshire equations, using this relative separation angle delta, we were able to successfully estimate our delta V during that separation maneuver, provided that we applied some additional constraints. Some future work with this, we want to continue doing an observability and sensitivity analysis, figure out what size changes we should be able to characterize, and look at some additional methods, possibly using some different filters like unscented transform or particle filters that might help us to do a little bit better job with this. And the other thing that I'd like to do is be able to estimate the time of the separation maneuver. So in this case, we had a truth data point, we knew what time we separated, but in general, it should be possible to say we've got these two objects, when were they close together or right next to each other. Last bit, I would like to acknowledge our partners with the U.S. Air Force Academy Falcon Telescope Network, and in particular, Francis Chun and Casey Schutz Christie. They've been very helpful with us doing maintenance and operating telescopes and helping us get the data back. So I would like to thank them. And with that, I'd like to thank everyone for your attention and be happy to answer any questions.